All right. What did we have? We have an economy of $10,000 per person output, per person income, with investment going at 4 units. The rest goes to consumption, 6 units. And I know that in this economy, K is equal to 2. And this is more or less all I have for you. Starting from the minimal set of macroeconomic observations, the minimal necessary data that we have, invoking certain additional assumptions like the classical saving function, like the exploitation rate had been resolved and given, and that's how the economy operates. We have completed a Marxian characterization of this economy and found a long-run equilibrium. Now, we are in the neoclassical world. Neoclassical explanation into the inquiry of what explains wealth of nations, what explains 10 units of income per output. How can we explain the wealth of nations from a neoclassical perspective? Our wealth or income is 10. How do we explain this? And as I had mumbled in the last 5 to 10 minutes of Monday's lecturing, what we do is first we impose the equality of investments with savings. That is investment per labor for that is little I investment per labor is 4 units, and total S is S times Q, or let me write this way. Savings per labor is saving rate out of output. It's not saving labor ratio. It's saving rate out of output. And I divide both sides, so I make output per labor. So if you divide both sides of this, I'm going to impose the requirement that investment per labor is equal to total savings per labor. And little s is total savings per output. Marginal propensity to save out of income. It is not savings per labor, right? Just let's make a differentiation. So if this is the case, then savings per labor is equal to little s times per capita production function f of k. This is my first introduction, or first intervention rather, my first intervention as a neoclassical modeler. Investments is equal to savings. And I have done all of this to remind you of the notation. Savings per labor, little s times f of k. Secondly, Q is produced by a neoclassical production function, and I assume that my production function is our good old a k to the alpha. All right, let's kick the road. What do we need to know? Well, I have introduced an unknown creature into the system. Now I want to understand how it behaves, what it is composed of, etc. First of all, from the data, I have to calibrate these parameters. These are unknown parameters. One elegant way is collect time series data, collect all these. This is my last observation, but have at least 20, 25 observations on this, run a regression, check the econometric diagnostics, and come up with an estimate of alpha. And then by knowing alpha, you can always find A from your data and get estimate of the unknown variables along with some confidence intervals. We do not have time. I am too old for this. You are impatient. And after all, this is, lads, this is all we have. We don't have time series data. Do whatever you want to do. Well, okay, then I come back and resort to theory and know that from the properties of this Cobb-Douglas production function, alpha is known as the share of capital in income, in total output. That is R plus delta times K divided by f of K. This is what alpha is all about. Well, in this economy, by the way it operates, we know that depreciation is full, 100%. This economy operates with throwing seeds as investment, and they become capital the next year. But in the meantime, capital of the previous year disappears under earth. It rebounds again as corn, but there are no seeds that I can collect from it. They become corn. It's desirable. Seeds had become corn, but seeds are, you don't have no longer seeds. So last year's capital had evaporated. They become something else, which means I cannot carry on last year's seeds as capital and use as seeds as this year's capital. I have to decide again to split the corn into savings and consumption. And then this property means that in terms of notation, note or remember, investment in this economy is next year's capital. Last year's capital is lost. The implication of which is that delta is 1. So I know delta. Do I know R? Yes, from my equilibrium equations. R is equal to 1 minus V divided by V times L over V times W. That's an identity relation. Or it is derived from an identity relation saying that value of a product is equal to wage costs plus profits. And given that identity, V is capital output ratio, and L is labor output ratio. And I know these. Good.
According to this model, I have to form new capital in each time period, right?
Exactly. 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 Now, technically speaking, this equation that is 1 is equal to L times W plus 1 plus R times V, that is the price cost identity, can be solved for R as this one. I have calculated in the meantime V as capital per labor divided by output per labor, which is 2 over 10, which is 0.2. So V is 0.2. L is the inverse of Q. Little l is 1 over Q, 1 over output per labor. It is the labor output ratio. And this is 1 over 10. So this is 0.1. And from that way onwards, this is 1 minus 0.2 divided by 0.2 plus 1 plus, plus L over V, and L is 0.1 divided by V is 0.2 times the wage rate. And for the wage rate, we again assume that we are in the golden, or we are heading for a golden rule. That is, I want to take wages to be driven to the subsistence consumption basket, just to clarify my way. So I'm going to take W as 6 units. So from here, I get R to be equal to 1.
Is that a minus?
That must be minus, that's true. That's true, yeah. That's the wage profit trade-off. The higher is the wage rate, the lower the profit. It had to be minus, thank you. So coming back to alpha, so we have delta equals 1, R equals 1, capital labor ratio from the data 2, and output Q from the data 10. So once you get these, you have 2 by 2 divided by 1. This is 0.4. Alpha has to be 0.4. Now, before going on anything, let me clean this. First of all, let's decide where we are. Since the net profit rate that I have just raised, since the net profit rate is positive, that means we are not in the golden rule yet. Because, as you know, the golden rule steady state is where the net profit rate is 0. As long as there are positive rates of return, capital accumulation must continue. So under steady state, or under neoclassical equilibrium, it must be true that S times f of k must be equal to delta k. Well, to continue with this operation, I have found this to be as 0.4. Now I have to state A. Well, A is Q divided by k to the power alpha, by simply moving around these terms. Q is A k to the power alpha. Therefore, A is Q divided by k to the power alpha. Well, what is Q? 10. What is K? 2. And to the power 0.4. From here, we read that this is 10 divided by 1.32. This is what 2 to the power 0.4 is. And alpha turns out to be 7.576. It's some number. It's what we call this as a calibration variable. It picks up the unknown residuals, and it is known as the Solov's residual. It picks up all things that explains producing 10 units of labor, 10 units of output by using capital and labor as a ratio of 2. anything unexplained needs a residual to fulfill the gap, and we call this productivity. Total factor productivity, unexplained, taken as given, but it is there to exist. What we assume is a number, and it stays constant as a number. So A dot over A is 0, but A is this funny looking number. And it will always be a funny number, up to 6, 7 digits.
Models that we know.
Well, let's put it this way. It is unknown because we do not know how to explain this, but it exists out there. We cannot explain how it behaves or why is it that what it is. We observe it, it's out there. In this economy, when you use 2 units of capital per labor, you get 10 units of output because there is some invisible God's hand that is helping you multiplying every little k by this variable to the power alpha, and you get output. It happened. Either I take it exogenously and say that, well, there is exogenous rate of productivity change. This number grows by 2%, 5%, 10%, X% over the year, but it is funny. I cannot explain why this number is out there in the first place. I cannot dare to explain how it behaves over time. After the midterm, we are going to solve for models, human capital, education, R&D, public capital, infrastructure, geography, distance from the equator, the fact that you are using Latin alphabet or Chinese alphabet, those sorts of things, to be able to explain a positive rate of growth on this. Right now, I only observe as I observe data, and from the data, I say that the level of technology and institutions is 7.576. What do you mean? Nothing, forget it. Just keep it as it is. That's our attitude now. Any other hard questions that require funny answers? Okay, let me continue. So my function is this. Our function then looks like this. Output is 7.576 times k to the power 0.4. So whenever you change k, you take a power to 0.4, that's by alpha, and multiply everything by this 7.5, and you get output. So let's impose this under the steady state. Little s. Good question. What is little s? S is total savings per labor, or it is equal to total savings per labor divided by Q per labor. Do I know total savings? Or do I know savings per labor? I don't. As a neoclassical economist, I cheat and say that savings and investment are identical. If you were a Marxian or a Keynesian economist, at this stage you have to define another savings function, like workers save this much, capital save that much, that sort of a thing. But as a neoclassical economist, you say that savings per labor, well, it's identical as investment per labor, which is 4, divided by little q. So this is little I divided by q. That is what savings is. If you were in the golden rule, peki şu not alma gerginliğini bitirin, ondan sonra soralım. Is everyone relaxed? If I told you that we are going to a golden rule, that's our rules and regulations, and you already know that alpha from the data had been calculated as 0.4. Could you have guessed the saving rate? Yes. Saving rate as a golden rule regulation must be equal to alpha. And bu herkes haddini bilecek rule. Capitalists will know that they are capitalists. Therefore, they are going to convert all their income, share of income, to investment, which is synonymous with savings. So once you calculate this, this is 4 over 10. This is 0.4. But you don't have to do anything. You could have only said that, well, as a golden rule behavior in this economy, since we are operating under the consumption maximizing golden rule behavior, saving rate must have been equal to alpha. If out of this exercise, if you arrive at a different saving rate than what you had done over here, and if you think that you are in a golden rule setting, then there must have been a mistake. So saving rate and alpha is 0.4 in this equation, in this economy. So we impose steady state 0.4 times f of k, which is A. What was A? What did I do with A? Anyway, A is 7.576 times k to the power 0.4. This is my f of k function. Must be equal to delta, and delta is 1. 1 times k. This is the solution to the steady state equation. That is S A k to the power alpha is equal to delta k. I want to choose a new capital labor ratio that satisfies the steady state, knowing that S, A, alpha, and delta are all parameters. These are funny looking numbers. I apologize, but that's how world is. This 0.4 times 7 becomes 3.03 to the power k to the power to k to the power 0.6. This thing moves to the other side, and k, all these stars, is 0.3 to the power 1 over 0.6, which turns out to be 6.348. This is our new k under the steady state. What happened? Well, geometrically, this is what had happened. We have had Q and K space. We have had the production function. We said that Q is equal to 7.576 K to the power 0.4. That's what that function is. We also had a 45-degree line which said that delta K, which is equal to 1 times K, that is delta K equation with delta equals 1. And then we have imposed the steady state with the property that S is 0.4 and pardon, şurada birisi beni arıyor. Neyse. With the property that we are imposing the golden rule, and under the golden rule, under the steady state golden rule, it must be true that f prime is equal to delta. So the derivative of the production function must be equal to delta. That is the property of it. So let's find out what the derivative is. F prime k is equal to alpha a k to the power alpha minus 1 with k is equal to 6.348. So f prime is alpha 0.4 times 7,576, 6.348 to the power minus 0.6. And if you calculate this, you must have 1. If you do all the arithmetic right. Which means that R, which is f prime of k minus delta, is 0. So here we do an f prime which is equal to 1. That means these two lines are parallel. And here is our maximum consumption, where the belly is at its biggest. This is my little c, maximized. You come down. This is our k, which is 6.348. And this is the output we produce. Well, how much output do we produce? We look for the optimal output level, which is 7.576 A times K, which is 6.348 to the power alpha 0.4. And that number turns out to be 15 units. 15,867. This is how much this economy is producing under the steady state. Any questions until what we had done thus far? Where were we to begin with? We started from an economy with 10 units of output and capital labor ratio being 2. We ended up in an equilibrium where K is 6.3 something, output under optimal equilibrium to be 15 units. We started somewhere from K is 2 somewhere. This was my original place, upon which I have constructed a Marxian equilibrium, and now I am constructing a neoclassical equilibrium. And this much of K had produced this output, which was 10. This was my original start. Consumption being 6 units, and the profit rate back then, the tangency at this 6 point units, f prime was equal to r plus r being 1, delta being 1, the derivative of the production function being 2. As a result of diminishing returns, I have accumulated capital, the derivative has fallen, and it became 1. That unit is used entirely by depreciation. Marginal product is exhausted, and you have no new net profit rate to go any further. We have accumulated capital starting from a gross rate of return of 2 units. This had stimulated the animal spirits of entrepreneurs. They have accumulated, and the economy has experienced a transitory growth under transition to the steady state, and over here it stopped. What is the amount of consumption?
9.9.
Excellent. How did you get it?
Çıkardım.
Neyi nereden çıkardınız?
Q, optimal Q minus optimal K. Büyük çıkardım. Yok.
Dur. Optimal Q'dan you have to deduct this one. But this is not. This is 6.3. What is this?
Equal K.
Delta K. Tamam. All right. So 1 times K. This is delta K. This is 1 times 6.3 for 8, and you said that this is 9 point something.
Yes. No, I see it as just 1K.
Tamam. 1 times K, and K is 6.3. So this is 9 point. All these numbers. 519. This is one way. Easy way is, or this is easy as well. I'm not disputing it. Another way is consumption is 1 minus S times output. Output not saved. Output is 15.867. S is 0.4. It had not changed. So this is 0.6 times 15.87 and this turns out to be that particular number. But it's the same thing, right? Total output 10 minus delta K, this much, and this is the remainder. Quick question, quick answer. What's the wage rate? 3, 2, 1. What's the wage rate? 100.000, 9.999, 9.998. What's the wage rate? Quick question. Evet. 9.5. It's equal to consumption. Wages is equal to consumption.
Because it is consistency level.
Subsistence. Bravo. Because wages are always at the subsistence consumption level. Whatever consumption is, wages are driven to that magnitude. So wages is C, and it turns out to be that magnitude. What was it? It was 0.2 in the beginning. What is it now? K divided by Q, and this is 6.3, that number, 348, right? Divided by 15, 867. This turns out to be 0.4. So what happened in the meantime? We started from this original value, original data, characterized by this, 2/10. It had become a new V. V has adjusted in Harrod-Domar's language. N is equal to S over V. This Harrod-Domar balance equation Holodomor's question is resolved by holding saving rate constant, assuming no population growth, and now V has to be equal to, pardon, let me clarify this. Let's use the full Holodomor equation, which is delta plus x plus n in its fullest sense. N is assumed to be 0. Technological change is assumed to be 0. And delta is known to be 1. So the Holodomor's stability condition had been met by changes in V. V has adjusted over time through technological change, and in the long-run equilibrium, it produced the Holodomor equation with V is equal to 0.4. That's how this economy has operated. In the meantime, nations had converged to this critical, optimal, glorious capital-labor ratio. Consumption is maximized. There is no such a thing as exploitation. There is full harmony. Anyone who embraces globalization is enjoying maximum consumption all over the world. And this is a tremendous World Bank, IMF annual report with all poor nations are going towards a maximum consumption on this planet. Everyone is happy. Anything else? On Monday, 5-minute quiz. Remember, that's what we agreed last day. And then I am going to play around with this economy, asking, what if there is unemployment in this economy? What will happen to the adjustment system? Whether will the workers be ever better off?
Wages will increase. Maybe.
Well, it's not maybe actually. That will be the mechanism to characterize the unemployment. Suppose that wages are here 9.5 units, right? That's what wages are, 9.5. Suppose that the workers had organized and there are approaching elections, and the candidate had said that asgari ücret will be double of what it is. So I have supposed that rather than 9.5, I'm going to set wages as 2 times previous wages. Put a minimal wage low where, and I will still be operating with the same production function, same saving rate, same depreciation rate, but offering higher wages.
And I guess wages doesn't equal consumption.
Well, it mustn't be, but you are paid more wages. And then we are going to pursue this theme, play around with it, and wrap up the whole subject. Peki, herkese iyi hafta sonları şimdiden. Stay out of trouble.